Hi, everyone. I'm Curran. I'm thrilled to be giving this presentation. So we'll be here for the next hour together. And it's going to be, I'm going to lead with a lecture of sorts about Choropleth maps and dot density maps. And then towards the end, I'm going to do a live coding session where we build a multivariate Choropleth map together. And I'll try to make some time at the end for open Q&A if we can. Some thoughts about multivariate Choropleth maps. First of all, who am I? Just a little bit of background. I'm a lead design technologist at Stamen, a consulting firm out in San Francisco that does a lot of client services, data visualization, and mapping projects. I also teach an online graduate course on data visualization at Worcester Polytechnic Institute in Massachusetts. I created VizHub, this platform for coding in the browser, and that's what we'll be using for live coding today. And I have a lot of stuff on YouTube. This is maybe how some of you have heard of me. So this has been, I've been working on this for like a year or so, and I just love teaching. I love open source. One might call me a D3 addict. I just love coding with D3 and all the amazing things that it can do. So this journey of mine began a couple weeks ago where I just got intrigued by the idea of dot density maps. Here's an example of a dot density map. It's census tracts in New York City that shows, or rather census blocks, that shows ethnic distribution. So here's the color legend over here. These different colors correspond to these different ethnicities. And you can see very, very clear grouping patterns. So I'll show a couple more of these. This is another dot density map zoomed out of the entire US of, I think, the same data. And by the way, before I get too far ahead of myself, I want to make sure everyone has the link to these slides and can follow along. Here we go, here we go. Yeah, so everyone should be able to click this and see these, and each of these images that I'm going to show is a link that you can click and play around yourself with. Yeah, so this is done with a Python library called Data Shader, and this is a zoomed in version of that same thing, again in New York City. And the reason why they call it a dot density map is because when you zoom way in, it's just a bunch of dots positioned inside of these polygons, essentially randomly. And then the colors are blended together in a certain way so that you have this perception, essentially, of one color for each of these areas. And here's another example from Wikipedia, Black versus Latino. And one dot is 1,000 people in this example. Here's a work that Stamen did, dot density maps in San Francisco, where you have trees, crimes, and cabs. And what sticks out about this one to me is the blending, how you can see that the colors are blended together. So I think the choice of how you blend the colors together has a big impact on the visual outcome. Here's another cool example that I found. Religious identity in Greater London. I mean, you can see very, very clear clustering patterns here where there are little communities within London. For example, I had no idea there was a Sikh community in the west of London. Fascinating stuff. So with all of these dot density maps, I got to wondering, you know, if you wanted to figure out the color that you see in one of these shapes, how would you do it? And the idea being that instead of rendering millions of tiny little dots, you could just figure out what color that the person would see and render that color in the polygon, essentially making a Choropleth map. So a Choropleth map is a map where you have polygons that are filled in with a single color. And this one is a recent piece by the New York Times, amazing, amazing piece that shows a detailed map of the 2020 election. And this is, although it's different colors, it's actually a single variable that it's showing here. So the red means Trump won, the blue means Biden won. And this is just amazing. The zooming and the panning is extremely performant with this map, which I'm so impressed by. And you can see, for example, in New York, very, very clear clustering within the different boroughs. Fascinating stuff. So this is an example of a univariate choropleth map, a single variable, but it's a diverging color scheme. Here are two other examples of choropleth maps, smoking in the US and obesity in the US. This brings to mind the phrase, get it right in black and white, which I swear by. It's amazing. So it doesn't need to use colors per se to be a choropleth map. So this, if you add another sort of level to choropleth maps, you come up with this notion of a bivariate choropleth map. If you take these two choropleth maps and give them different colors and put them on top of each other, you can come up with what's known as a bivariate choropleth map, where the color legend looks something like this. Little smoking and high obesity gets one color. Lots of smoking and low obesity gets another color. And lots of smoking and high obesity get another color, which is a combination of those two other colors. So you can see a lot of interesting patterns with this approach. Here's how it basically works. Variable 1 goes in the x direction, and variable 2 goes in the y direction. And you sort of overlay them and blend the colors together. And you get this color legend for a bivariate choropleth map. And here's an example that uses that particular one. This is percent insured versus donations. I don't know the context of this. It's just an example that I found. And again, each of these images are links that you can click through yourself to get at the source of these things. So this is another quite good illustration of the concept. You know, you make one choropleth, make another one, blend them together, and you get a bivariate choropleth map. More examples, percent covered by Medicaid versus percent voted for Trump. Another example, Black and Hispanic. This is quite striking to me because you can see some very, very clear patterns here, geospatial patterns. Fascinating stuff to dig into. Here's another example, income and inequality. Again, I don't know the details, but I'm just showing a lot of examples to demonstrate that you could apply this technique to all sorts of data. Here's a good one, wine versus beer. The purple is people who spend a lot of money on wine, and the orange is people who spend a lot of money on beer. So I think it's just fascinating to see, you know, East Coast, West Coast, people drink a lot of wine, but in the middle of the country, people tend to favor beer. Fascinating stuff. Here's some work that Stamen has done. This one is from this super diversity project that studies various intricate patterns of various types of diversity, particularly in cities. So this is the city of Vancouver, where it's income diversity versus ethnic diversity. And you can see quite interesting patterns here using this approach. Here's another example that Stamen has done, the UCSF Health Atlas. This is a quite impressive tool. If you click through it, you get the interactive version where you can see its California census tracts. The blue color ramp is white, and the yellow one is Latinx. And there's some cool hovering interactions here as well. But that's sort of tangential to this presentation, but it's a very cool effect. And then approaching the level of dot density maps, what about 3 variables on a choropleth map? How would you do that? This is actually a thing, and it's called Trivariate choropleth maps. Here's an example by Alan McConkey, who also works at Stamen. We are colleagues. This is the famous pop versus soda versus Coke map. It's different places in the US and what word people use to refer to, carbonated beverages. Trying to avoid using one or the other. But yeah, it's quite fascinating. And this is the kind of color legend that you would come up with a trivariate choropleth map. Each of these counties falls in one of these little triangles and gets color depending on that. People often make the argument that multivariate choropleth maps are hard to read because it's hard to position these. But I would argue that if the data has this quality of very strong clustering where each place has a majority in one or the other of these, then it's quite easy to read. You can see very clear clusters of like, okay, right here, people use the word soda, and all in the South, people use the word Coke, and all in the northern part of the country, people use the word pop. Here's another example of trivariate choropleth reading, writing, and earning money as 3 different choropleth maps that are essentially layered onto one another. Then you get this trivariate choropleth map. Here's another one, percent smokers, percent obese, and percent excessive drinkers. And I love the labels on this map, like stark increase in drinking. Over here it says elevated obesity and smoking. Nice annotations. So that's sort of a survey of what people have done. We're about 15 minutes in, so we've got 45 minutes remaining to do some live coding together. So here's what I was thinking. We start with this thing that I have made in the past. It's a choropleth map of New York census tracts based on this American Community Survey data from the US Census, which contains data about demographics. White, Black, Native, which means American Indian and Alaska Native, Asian, Islander, which is Native Hawaiian and other Pacific Islander, and some other race. So this type of data is ripe for building a multivariate choropleth map from. Just a little bit of orientation about where this code came from. So this is inside of VizHub, by the way. And if any of you have the slides open, you can click through this link and get to the same editor. And then if you log in and click fork right here, you can follow along and edit the code with me. And I would encourage you to do that if you're up to it. So where did this code come from in the first place? In VizHub, you can click on what it was forked from. And in VizHub, by the way, the only way to create something is to fork something else. So if you trace the lineage of what this was forked from, you can trace it all the way back to this one, Cheap Tricks for Interaction, which I have a YouTube video about, where this is coded from scratch. So if you want to, after the session, learn about all the details of this code, you can watch this video to get maybe 95% of the code. So I adapted it to, to work with this New York data. So let's begin. I'm going to start by forking this viz, and I'm going to say, I can rename it here to be multivariate choropleth. And let's see, just before we begin, I'd like to just get into this description a little bit. I added a description of what this is. This starting point is an intermediate state on the way towards a multidimensional choropleth. The more green it is, the more white people there are in that area. And the way this works is that it uses a linear scale, a D3 linear scale, that varies in opacity only. And here's the little code snippet that defines the color scale for this choropleth map. It's a linear scale where the domain, the sort of data space of this, goes between 0 and the maximum of the white value for each of these rows in this ACS data, American Community Survey data. And the range of this scale, the screen space, so to speak, the colors, they are 2 colors that only vary in the opacity. So RGBA is a way of expressing colors in web graphics. So this is a red, this is green, this is blue. These all vary between 0 and 255. But then the last field is the alpha, or the opacity. And so the starting point has an opacity of 0, which means totally transparent or see-through. And the maximum value corresponds to a color where it's totally opaque. And so we're seeing this gradation between white and green, but the whiteness is actually because these shapes are semi-transparent and it's sort of fading into the background. And I could just demonstrate that real quick by just setting the background color of the body to be black. And you can see clearly that, okay, it's not set to go from white to green, it's set to go from transparent to green. And I set it up this way so that we can blend these colors together once we have multiple different scales. And I actually kind of like the dark mode look, so I think I'll just keep this like it is. Let's try to do this. I'm thinking, in addition to having a white scale, we can have another one. Let's just pick a variable. How about black? So we can visualize white versus black density using a multivariate choropleth map. So I would start by copying the definition of this scale, and then let me just get some more space here to work with, and then renaming it from white to black scale. And it was complaining for a second that it was defined multiple times. I'm going to go into this mini mode here so we could just focus on the code. So what I've done is I've copied this scale definition, and instead of the domain using the value for white, we can change it to use the value for black instead. And instead of using this RGBA value, we can use something else. I'll just pick another color. And I like to use the Chrome DevTools to do that sort of a thing. See, we can use this little color picker in here. Oh, but sometimes it doesn't let you do it if it's inline. So here's what I can do. I can just say fill is some color, and then I can get this color picker. Boom, there we go. So let's pick what color we want for this other value, the black value. I'm thinking we just make it vary in the hue, and we pick a hue that's substantially far away from green so that they could be easily distinguished. And by the way, this is actually changing the color of that one little element there. That's the magical thing about the Chrome DevTools. So maybe this like orangish value. I think I'll try that. It's substantially different from green. And with this little color picker, you can get these different formats. And so it has actually RGBA. So what I'm going to do is use this value of R, G, and B in our definition of the color. So it's 255, 71, and 0. So over here, I could just type it 255, 71, and 0. And we want to use that same hue, or that same color, varying between totally see-through and totally opaque. Now, the problem is the fill is just using that one scale. It's just the white scale. but we want to also use the black scale as well and like mix the colors together. So we have to somehow modify this function right here. As a start, I'm going to change it from being an implicit return to an explicit return. That way we can have multiple statements in here where we combine the output values and then we return them. So the indentation is a little messed up. I'm just going to click this little P to use prettier to auto-format this code. So now we're in a position where we can do something with the black scale. So we can invoke black scale and pass in the value black for that scale instead of white. And now we have two different colors essentially. So I'll make a new variable, black color, white color. Kind of awkward names, but that's okay. And so this would be the output from the white scale. So now we want to somehow return a combination of these two. And the question is, how do we combine these? So we get black color. I mean, ideally, we could just say black color plus white color, but that's not really a thing. That doesn't really work. That would just do string concatenation. So somehow we want to like blend these colors together somehow. And I did come across this library called Blend JS or Color Blend. There it is. Color-Blend. It's this open source library that does color blending in JavaScript. And here's how you use it. You import a blending mode such as normal, and there's a lot of other blending modes that we can choose from this package, Color Blend. And when you define colors that are the input for this, it has to be an object with R, G, B, and A. So part of our task is going to be to generate these from our color strings. And then you can just invoke the blending mode with these two colors. And it returns another one of these objects with R, G, B, and A. And then we can convert that into a color string, a CSS color string, so that we can render it, on the map. So this is going to be what I'll try. And this is a nice little illustration of the blending, what it looks like when two colors blend together. So back in our code, we're going to have to pull in this library somehow. And notice that it's published on NPM under this name, color-blend. And because of that, we can use a CDN like unpackage to pull in this library. And it's a very small library, beautifully small. This has UMD in it, which means universal module definition. So that means we can pull it into the browser and it's going to work. So what I'm going to do is just copy this URL, and over in our code, I'm going to modify index.html, which is already pulling in these two libraries. I'm going to modify it to also pull in this new library. So I'll add a script tag, pull in this thing, and that should give us a global variable called color blend camel case. I think it should. Let me just see if it does. Console.log color blend. Okay, that's there. It's defined. It worked. So that's great. We got the library. Now we can just call color blend dot. See, these are all the different blending modes we could use. Maybe I'll just try normal. We can tweak the blending mode later and see what the best results are. So we want to actually call color blend dot normal to blend those two colors together. But remember, we need to convert these into objects. We can't just pass in the colors themselves. Let's just see what these are. I would guess they're going to be RGBA color strings. Let's just find out. Yeah, that's what they are, RGBA color strings. So we need to somehow convert these into objects that have R, G, B, and A. How would we do that? Well, so it turns out that D3 has a color module, D3-color, and this is bundled inside D3. So anything in here we can access. So what this does is it lets you instantiate these color objects, which have properties depending on which color space it is, like RGB and A. And I believe there's one for RGBA, or maybe it's just RGB. Or wait a minute, just D3 color, D3.color parses the specified color string and returns a color. So let's try this. Now remember, our goal here is to produce the input required for this blending mode, which means RGB and A. So let's see how close we can get to that with this D3 color thing. So the way we would use that is call color with a specifier. And the specifier, by the way, is this RGBA color string. So we would invoke it like this, and we could call it like this, D3.color, but I personally prefer to use ES6 imports. So we can import color from D3 along with all this other stuff that's already being imported. And then we can console.log that and see what we get. What do we get if we just pass the RGBA color string into D3.color? Let's check it out. All right, see that? We get this object. We get an object that has R, G, B, and opacity. That's not quite what we need, because this color blend library requires that it has A instead of opacity. So I think what I'll do is I'll just write a little function that will generate these objects. I'll just define a little function right here. I'll just call it RGBA, or how about 2RGBA? And this will be a function that takes as input something and returns something else. And that input, I'm going to use ES6 destructuring here. It's going to have R, G, B, and opacity, because that's what the D3 thing gives us. And what we're going to return, I'm going to use this implicit return and return an object that has R, G, B, and A set to opacity. This is just a little plumbing that we need to do to make these things talk to each other, interoperate. Again, I'll use prettier just to format this. And then we can call 2RGBA on the output of color, and now we should get objects that have RGB and A. Let's check it out. There we go. Okay, perfect. Now, this is what we could pass into that color blending thing. So if we just pass in to color blend.normal 2RGBA color of black color, and then 2RGBA color of white color, it should work. Paste white color right there. And let's see, what is going on here? Some kind of an error. Unexpected token.
And you mean some closing brackets?
Yeah, I need another closing parenthesis. Oh, a couple more, actually.
Another one.
There we go. Now, it's not...
In the first two RGBA, and there is another missing bracket. Just like here.
Whoa, that's an awesome little annotation. That's so cool. Boom. Wow, Zoom for the win. Thank you so much. That is totally correct. I put the parentheses in the wrong spots. Yeah, so now it's these two. This is a single thing. This is another single thing. All right, and you know why this isn't working? Because this is giving us an object that has RGB and A, not a color string. So we need to convert this again to a color string. And I don't know, does this library have some utility to do that? I don't think so. It's just focusing on the blending. So we're going to have to do that ourselves. So let me write another function to go the opposite way. Since it's the opposite of 2RGBA, I'll call it from. RGBA. And this is going to take as input an object that has RGB and A, and it's going to give us as output a color string. So we can use this ES6 string template literal syntax, where we can give it a well-formed CSS color string that looks like this, RGBA, and we pass in R, G, B, and A. And this syntax just substitutes the values of these variables into the string. And so just to get a sense, we can console.log from RGBA of, we'll call it blended color. And blended color, we can make a variable here and set it to be the output from the blending operation. And then if we log that out, this is what we see. These are the well-formed CSS color strings that we need. So now, if we just return this instead of console.logging it, we should get a bivariate choropleth map. Boom! Now, let me see if we can make a trivariate choropleth map by extending this approach just a little bit. So let's say we want to visualize something else like Asian. We can do the same pattern where we introduce another scale in addition to black and white called Asian. And we return d.asian to get the max. Although now that I think of it, these are using different max values, so it's actually a little misleading. Ideally, they should all use the same max value. So let me just address that right now, because it's not accurate. Because like if the max Asian value is like 10%, we don't want it to be a full opacity. It would compete with the max value for these other ones, which may or may not be the same. So that's why we should use a global maximum for these different scales. So before I go any further, let me just define a variable called global max. And this is going to be max, which is a D3 utility, where you can pass in an array and it computes the maximum value of those array elements. And it'll be the max of white, black, and Asian. And then we can use this global max as the second value of our domain for all of these scales. This is more conceptually accurate. Okay, so now we can pick the hue that we want to use for the Asian colors. So let me get in here. Can't use that color picker. So again, let me just say the fill is this color. Then we get this color picker. And we can pick another hue that is kind of far away, maybe like something like this. So that's 204, 40, and 154. 204, 40, 154, just so I remember it. And this is going to be our Asian color here. Now what we can do is compute another color for Asian. Actually, you know what I'm going to do? I'm going to use the Vim utility here and just select this line and do a replacement. So now we have Asian color here, and we can blend these things together, but I believe the blending function only takes as input two things. So let me use let here, because I'm going to reassign blended color to be the normal color blend of the blended color and the Asian color. This is how we can blend three colors together. And I think, oh, I didn't assign it. So yeah, blended color equals that. Now we should get three variables here, but it doesn't really look like it's working. There may be something a bit off here. Let me just console.log these two inputs to make sure that they're valid. Those two things, they should be the same type of thing, and they are. Okay, that's good. That's good. What did I do wrong here?
Are you sure there's a lot of Asian people? Maybe there are three colors there.
Yeah, actually, this one has a pinkish tint to it. Yeah, maybe it's working. It is working. Look at that. Yeah,
There we go.
we've got three distinct different hues. Yeah, yeah. Okay, it is working. Great, great, great. Fantastic. So, I mean, we could go a number of different directions with this. One thing, I was researching about blending modes, and I learned that the normal blending mode, rather, with the normal blending mode, the last one could potentially clobber all of the others. So the ordering of the blending matters, but there are other blending modes where the ordering of the blending doesn't matter. And so let me just show you what it would look like to experiment with different blending modes. I'm going to say there's a function called blend that's going to be color blend dot normal. This is so that we can change it in one place and it'll be used everywhere. So we can use blend here and, oh, there's a console.log. We don't need that anymore. And we can use blend here. And now what we can do is change normal to something else like multiply. And we get a slightly different result. And we can play with the different ones that are available in this library. There's multiply, screen, overlay, darken, all these different things. So let's try, I don't know, overlay. And we get, again, a slightly different result. But you can sort of see that there are patterns here. And another thing that might work well is trying a different type of scale. Like instead of scale linear, what if we used scale square root? I can do a global search and replace for scale linear and replace it with scale square root. And we get a much more vibrant map. And this is all sort of territory that I'm really just exploring. I don't know if there's any best practices around this regarding the types of scales to use or the blending modes. So I'd be happy to, continue a discussion around this sort of stuff after the fact with whoever's interested in this sort of thing. I think multiply might look good with the square root scale. I don't know. So that concludes the live coding portion. I'm thrilled that you all are here listening to this. And I'd like to open it up for just an open-ended discussion. Feel free to ask me any questions.
I'm super impressed that you live coded D3 and everything didn't blow up. That was awesome.
Thank
so
you.
it's not a question, but thank you.
The trick was I had coded it like last week to just make sure all the steps, taking inspiration from Bob Ross, who actually did a version of his painting before the camera was rolling to work out the whole sequence of events and then do it again live. So kudos to Bob Ross for that idea. Any other questions?
I have questions, but are more related with the data shader thing you talk about.
Sure.
How does that technology works? Is it difficult to learn?
I really don't know. I just came across an article about data shader and I thought it was super cool. I never actually used it myself. It's a Python thing, and I'm not really a Python person. I don't know Python that well. But I did attend a talk by the author of Data Shader that was quite interesting. And it really is inspired by shaders, as in real shaders that run on the graphics card, like OpenGL kind of shaders. And I believe it's an implementation of density maps using shaders, like real shaders. And I asked him how the color blending is done, because that was my main interest, so that I could approximate the color with this Choropleth approach. And he told me something like it's a weighted average of the dots or something. But beyond that, I really don't know how it works.
Can you also talk about how the polygons were made initially, like the ones you started working with?
Oh, sure. Yeah, that's a great That's a great little thing. Let me just go back to sharing my screen real quick. So what I did to get the shapes, it was actually inspired by this block from Mike Bostock. And this block, it's backed by a GitHub gist. And in this GitHub gist, there is a makefile. And in this makefile, you can actually run this. And what I did is I actually forked this to get the most up-to-date data. This is from 2012, and I'm using from 2019. So you can just use this makefile. You can clone, and this is what I did, clone this gist to my machine. And I can actually show this, why not? And the gist, this won't take too much time, I swear. I forked this gist, and here it is. So the gist is called, it starts with 08, and I think I already have it on my machine, 08 something. There it is. So if you see the files here, there's this make file. I changed it to use 2019 files from the Census. So the Census has this whole thing called Tiger lines or shape file. It gives you shape files, which contains the definitions for these geometries, these polygons. And so if you download this file, it's a huge file that is a couple megabytes or something. It's actually in this build. Yeah, you get a zip file that unzips to a shape file. And just to see how big these files are, the shape file is like 7 megabytes. Or yeah, the shape file itself, when you unzip it, is 12 megabytes. No way you can get that into the browser. So the approach that's taken here is it uses this tool called TopoJSON, or JSON. I still don't know how to pronounce JSON. And it simplifies it using a line simplification algorithm. Perhaps the Douglas-Boyker algorithm. And it also pre-projects the geometries in the command line. And so I tweaked this value of simplification to get something that's roughly a megabyte. If it gets to be like 500 kilobytes, the shapes are all like stained glass. You just lose all the detail. And if it gets to be like more than 2 megabytes, it's just such a big file. I wouldn't want to, abuse people's bandwidth, sort of thing. So if you just run make, I have to remove the build directory. If you just run make, it downloads the file, runs the simplification, converts it into a TopoJSON file. And so I would just do like a git add here, which adds it to this gist. And then here's this JSON file. It's one of these JSON files in here, ny.json. And then just take the raw URL, which is this TopoJSON file. And this is what gets pulled in from this code over here. It loads in this file from this gist. One of the files is the census tracts as a TopoJSON file, and the other file is the demographics JSON file, also from the census. So that's how the polygons are created.
Can I just ask one more thing as an add-on to that? Out of curiosity, are you aware of any libraries or something that can help you help us form those shapes and stuff? Because right now we're using like the pre-made one, but if I want to do it for something that doesn't exist for an area or something, like a country.
Sure. I mean, that makefile uses TopoJSON, which is a command line tool that does this simplification and conversion from, I think it does the conversion from shape files to TopoJSON. There's a whole universe of tools that does this. Another one of my go-to tools, by the way, is Mapshaper. Mapshaper.org. You can just take a shapefile, which is usually the format that you get for these type of polygons. You can get shape files for countries, for states, for counties, for regions of any country. It's the most common file format, but they're typically huge, like 10 megabytes, 20 megabytes, because they're very detailed. you can just drag and drop them into Mapshaper and then simplify them. Let me just show you what that looks like. If I open up the files, we get this shape file, or rather a zip file. The zip file has all this stuff in it. You can just drag and drop this to Mapshaper, click import, and then you get this slider for simplifying, which is just beautiful. So you can see if you simplify it too much, you start to get this like stained glass kind of vibe going on. And you can drag it to simplify it as much as you'd like. And then you can just click export to get a topo.json file that you can load into your D3 code, and it should work.
Thank you so much. This was amazing.
My pleasure. Thanks for your questions. If no one speaks up, I'll go to the chat and just answer things that I see there. Someone says, I don't work with RGB. I assume the blending is more complicated than that. Simple math. Yeah, it is. That's the guy who wrote that library that does color blending. Spent loads of time researching it, and it's a whole can of worms. There's papers and stuff, specifications. So I never got so into it. I just used the work that he did.
There is another question in the chat.
Yeah.
When will the free CodeCamp live teaching start?
Oh, unfortunately, yeah. So I had this agreement, this idea with Free Code Camp that I would have this live stream series, but they ended up saying, oh, we're not going to do live streams anymore. We're just going to focus on videos. So I hope to do a live stream just by myself, kicking off hopefully this month, where I'll do like a weekly live stream of this same kind of a format. So I will, announce it when the time comes. Before we drop off, let me just drop my Twitter handle. That's where I'll be. I'm quite active there, so I'll just drop that in the chat. So just, I will announce every live stream that I do in the future. I haven't done one yet, but I hope to start them soon and make it a regular thing. All right, well, we're just about at time, so thank you everyone for attending. This has been quite a blast.